Well, thanks so much, Sheila, and it's so great to be here, and welcome to everybody on Zoom, and great to see everybody in person here. I'm so honored to have such a great turnout. And today I'm going to talk about, as Sheila said, some research that is from graduate school. It is slightly younger than the flood, so it was like 2006. So it was a while ago. But the flood happened just shortly before that, at least in geologic time, right? So a gush and a rush, catastrophic flooding from Ice Age Lakes Alvord and Coyote into the Owyhee River. And before I get started, I just don't want to forget to acknowledge my wonderful mentors and advisors here that really helped me get to where I am today. Dr. Lisa Ely, who is my advisor at Central Washington University. Some of you might know Jim O'Connor from Portland with USGS. Meredith Reheis with USGS in Denver, who kind of is the expert on pluvial lakes in the Great Basin, spent her entire career doing that. And Dr. Cassandra Fenton, she's now at Colorado Mesa University here. So it's so fun. As Sheila mentioned, I teach at Lynn Benton Community College, which is my dream job. I love it. One thing I love to get students excited about geology, but I don't get to do a lot of research. And so it's really fun to go back and revisit this. So thanks. So just to kind of set the stage today, I want to start out, and Sheila gave that nice introduction, which is a great segue into just kind of some larger floods that many of us know about already. And then we can kind of use that as a comparison for the flood that I studied here down in southeastern Oregon, and kind of present it through the lens of the scientific process of testing a hypothesis. We'll look at some of the evidence here of the flooding, the age that we tried to determine. We did some hydraulic modeling to determine the size or the magnitude of the flood, so we can kind of compare it with other large ice age floods, and then its significance as well. So I'm sure probably everyone in this room, or many of us at least in this room, are really familiar with the Missoula floods here, the spectacular ice age floods that happened 15 to 17,000 years, although there's some evidence that there may even be some older Missoula floods. And these were really caused by the damming of we had this big ice sheet, the Cordilleran ice sheet here at the end of the last ice age here, and a lobe of this ice sheet came down and blocked the Clark Fork River and created this huge lake here behind it, Glacial Lake Missoula. And the dam failed multiple times, maybe on order of 90 to 100 times. At least we have really strong geologic evidence of 40 floods for sure, and probably more. And those, of course, poured down through eastern Washington, and kind of all this brown area here is the channeled scablands, where that soil was just ripped up and the floods channeled themselves into the Columbia River. And then here where we are, right, the floods actually backed up the Willamette River here. So if we were here during one of the Missoula floods, 15, 17,000 years ago, we'd be under probably a couple hundred feet of water. I live in Corvallis and I teach in Albany, and we were under a big lake too. So that's certainly pretty impressive. And evidence of the Missoula floods can be seen all over the place. Some of my favorite spots are the University of Montana. And this is, you can see these lines in the back and where the big M is, and these are all strand lines representing different lake stands of Glacial Lake Missoula here. So think of these are like shorelines, right, etched into the side here in Missoula, Montana, representing some of the high stands of Glacial Lake Missoula. And as the as a flood came out, these things were just gargantuan. And we can see here, you've probably seen, if you've, just in the summertime playing at a creek or something, seen ripple marks in the bottom of a gravel channel. And we see those same things, ripple marks here in the Camas Prairie. And these are what we'd call scale independent, right? So they form the same process, but these are just gargantuan. You can see, here's a semi-truck for scale, how high these things were. And the floods, as they traveled through eastern Washington, they scoured out the Columbia River basalts. They created channels here, just plucking basalt. And like, these are the Drumheller channels. These weren't like there wasn't like a previous stream flood here. The floods did the work here and carved this impressive topography. And here in the Willamette Valley, well, one thing, I'm a native Oregonian, and it's another great reason to be here today. I actually grew up in Portland, and my dad is a PSU alumni. And I, so it's one thing. I went to college and I had no idea what geology was. I started out as an English major, and my advisor looked at me and she's like, "Oh, you need to take your science class. You should take geology." And I had no idea. I was like, "What was that?" And I took it, and I grew up a lot of hiking and cross country skiing, and I immediately just jumped onto geology because it really helped me explain the landscapes that I played in all the time growing up. So sorry, a little segue there, but one other thing I love about Oregon is that we have a state park just named after an erratic here, after a rock, basically, right? That's pretty great if you're interested in geology. And this is Erratic Rock State Park out of McMinnville here. And this is a huge rock here. This thing was actually rafted in on a chunk of ice in one of these Missoula floods. So it was carried in, you could think almost like an iceberg at the top of the floods. This thing is Proterozoic in age, and it's a metamorphic rock. You don't find metamorphic rocks in the Willamette Valley here. That's why it's called an erratic. It's not from here. And its age it's Proterozoic. It's like over 1 billion years old. And so you can find these scattered throughout the Willamette Valley. And most of these were ice rafted boulders that would have, again, we know ice floats, right? So it would have floated on this flood surface here. And then when that kind of iceberg settled out and the ice melted, these erratics were deposited. And they can give us kind of an idea of the flood surface, the height of the flood surface here. And so that's how we can tell places like where I'm at in Corvallis, like you can find these and tell that the flood, or at least as the flood traveled down the Willamette and backed up the Willamette, would have been about 200 feet deep there. Another flood, maybe doesn't quite get the same kudos as the Missoula flood, but equally impressive, I think, is the Bonneville flood. And so at the end of the last ice age, there were numerous what we call pluvial lakes throughout the Great Basin. And the biggest one here, you can see on this map, is Lake Bonneville. And it was huge. You know, it covered a substantial part of the state of Utah here. And its remnant today is the Great Salt Lake. And these lakes would have formed largely because these basins are closed. And so water gets in there, and really the only way for it to leave is mainly through evaporation. In this case, though, water left through a pretty major flood here. So we can see here, this is the Salt Lake Basin. We can see some strand lines here, some lake level lines like we saw with Glacial Lake Missoula here. And this flood here overtopped a pass here called Red Rock Pass. Sometimes we call these things sills. So picture like a sill is like the edge of your bathtub. Imagine you filled up your bathtub and you forgot to turn off the water. The drain was in, right? And it pours gushing out. And so this is kind of like you had a big bath. This was your bathtub that you forgot to your geologic bathtub you forgot to turn off. And so it pours out of the sill here and floods and kind of flows down through the Snake River drainage and eventually into the Columbia. This one's a little older, around 15,000 years, so it happened before the Missoula floods, but also had a lot of just spectacular flood features. Again, similar things that we see with the Missoula floods. We see huge boulders here. If you've ever been to Twin Falls, Idaho, you just step outside and walk around anywhere almost around Twin Falls, Idaho, and you notice basaltic boulders just riddling the surface. And those are Bonneville, those are boulders transported by the Bonneville flood. We see surfaces that are scoured and fluted by the floods here, just to really give us an idea of how big these things were, this particular event was. So of course, growing up in Oregon in the West here, I was really interested in floods here. And when I was looking at grad school, Lisa said, well, hey, Deron, do you want to go to Rome to do your research? And I was like, yeah, Rome, that's awesome. Well, this is the Rome, I was thinking of a different Rome. So not Rome in Italy, but Rome in Oregon, which is a tiny truck stop, basically. And it's right on the, there's a fantastic rafting trip, and it's right at the put-in of a nice stretch on the Owyhee River. And this here slide I just put in to kind of show the landscape that I got to work in and do this field area. And in Rome, there are the pillars of Rome here. Again, nothing with like the Roman Empire, but these really kind of cool layered. These aren't flood deposits here, but lake deposits from Lake Idaho, which way predates the flood. But really, what got me, so I didn't get to go to Rome, Italy, but I was kind of deciding grad school, and the thing that really got me involved in this was my advisor Lisa said, "Hey, Deron, if you decide to come to Central, I have a fully paid week-long rafting trip on the Owyhee River, and would love you to go on it." So that's how I chose. I was like, "Hey, how can I go wrong if I get a free rafting trip out of this thing?" So I went on. This is kind of my first recon in the area here with my advisor Lisa and Jim O'Connor, and it was kind of a geomorphologist's dream. It's like the dream team of geomorphologists on this Gordon Grant Kyle House. And we spent a week rafting, and part of it was we were looking at landslide dams and lava dams in the Owyhee River. But there was also this kind of recon work here that was looking a little at this other potential flood that would have flown into the Owyhee River. And so that was also kind of something that got my interest here. And I also just want to take a moment here to acknowledge, some other geologists that worked in this area or studied floods here. And as I spent a lot of time down in this area of southeastern Oregon here, I got to read some of the papers. This is I.C. Russell here, who was one of the first geologists kind of in this area here, and I pictured him riding around on horseback, maybe 100 years before I was there. And of course, this is J. Harlan Bretz, who is credited with the hypothesis of the Missoula floods. And then I had to put Vic Baker here, who has spent a lot of time really revolutionizing the thinking of catastrophic flooding. And the first time I met Vic Baker, he was introduced to me as my geologic grandparent. And that's because Lisa Ely, my advisor, Vic Baker was her advisor, and then Jim O'Connor, who was also one of my other advisors, he was Vic's student as well. So the first time Vic came up to me, Lisa and Jim were standing there, and they're like, "Deron, this is your geologic grandparent." So Okay, well, let's go on to the flood here, and onto the research now that we've kind of set the stage a little for some of these other big floods here. And this is the study area here. So you can see down in southeastern Oregon, here, this wonderful, super remote area. And this over here is Steens Mountain. And this is the Alvord Desert. And we'll get a sense of what all this looks like here in a moment with some photos. But the big picture here is we had one of these big pluvial lakes like Lake Bonneville. It was much smaller in volume to Lake Bonneville. And this pluvial lake spilled into a smaller pluvial lake Coyote, and poured down the Crooked Creek. And there was a Meredith reheist that I mentioned earlier, kind of came up with some of this initial idea that there might be a flood, and these might be the sources of it during Friends of the Pleistocene field trip. And so this is a kind of a yearly gathering of geologists. I know Scott is certainly part of it. There is a songbook, so you can imagine geologists around a fire with a song. We have a song leader here in the audience with a songbook, and then there's Pleistocene involved too. So I need say nothing more here, but this gives you an idea of the kind of an overview of the study area. So this is up on the Trout Creek Mountains, and we're looking in the back. You can see kind of maybe a little snow-covered peak here. This is Steens Mountain. And then kind of this gray area is the present day playa surface of the Alvord Basin. And then you can see the present day surface of the Coyote Basin. So if we could take a time machine back to the late Pleistocene, we'd see that these would be big lakes. We'd see water in here, and we'd see a smaller amount of water in here, but they wouldn't be connected. And Steens Mountain is really a spectacular place here. So this is a picture I took from the Alvord Desert here. I was really fortunate. There was a hot spring right around here that I would park my truck at and camp at, and then every day drive across the playa surface here to a field area, a 7-mile drive. So it's like the best commute to work that I think anybody's ever had. Steens have about 1,700 meter vertical relief coming up from the basin here. And they had glaciers. They had an ice cap during the last glacial maximum on them. And they really supplied a lot of the drainage for Lake Alvord. Okay, so you can imagine these glaciers melting, running off, filling up the lake. The lake's in a closed basin like a bathtub. And I know at dinner tonight, we talked to some folks that have been up to Kiger Gorge and some of these spectacular U-shaped valleys here that were just, you can imagine during the last ice age here, this thing would have been covered almost entirely in ice. This is a little coal right here. So this was probably carved as a little glacier poured over into the next valley here. So, we're looking at almost probably almost a vertical mile of ice right here from the top of Steens Mountain to the bottom of the Kiger Gorge here. Much different than today. So we're looking back at Steens Mountain, and this is one of the areas that my work commute here. So drive across the playa, and I came here because this was a really interesting area. I noticed this on air photos. It's this low point, this little saddle between the Alvord Basin and the Coyote Basin. It's called Big Sand Gap. And the Lake Alvord would have been, pretty long, again, pales in comparison to Lake Bonneville, but about 110 kilometers long, 60 miles long. So, a decent sized lake. And this here was an overflow channel. We think this was carved as the lake rose and spilled out, kind of like that bathtub, like we talked about with Lake Bonneville, spilled out and would have cut this channel here. And this channel would have moved into Lake Coyote here. So one of the things that we wanted to look at was figuring out the height of Lake Alvord. How high did Lake Alvord get? How did the lakes fluctuate? So we spent a lot of time around the edge of the Alvord Basin looking for evidence of shorelines like we saw behind the University of Montana. And we can see these shorelines etched into the side of the hill here. A nice, kind of flat surface. You can imagine waves lapping up here. And this shoreline here was at about 1280 meters. And we wanted to try to figure out the age of the shoreline here. And one of the ways we relied on it was relative dating. So we're not getting an actual number. It was this age, but looking, how does this shoreline's age compare to other shorelines? And we can look at things like soils. We can look at how the rocks are weathered, how much weathering there is. We can look at something called carbonate and look at the development of that on clasts here. And so we spent a lot of time digging into these to kind of assess the soils and to get the relative age here. And what we found is we had kind of 5 lake stands at Lake Alvord, and we had 2, the ones that were at 1,300 meters and above. Those are older. Those had the soils, the weathering characteristics. Those are older than these younger ones here that were in the 1,200, the high 1,200s. And this just gives you an idea here. This is right around Big Sand Gap, and you can get a sense here of the shoreline here, the nice kind of flat planar surface. So we found shorelines here that gave us that helped us kind of create a map like this. And then we went into the smaller lake basin, the Coyote Lake Basin here, to assess shorelines. And we found some shorelines here. You can see there was this would have been kind of a little island here that had these really kind of rounded, sub-rounded cobbles on it that would have been rounded by the lake lapping up on it and weathering it here. And we found 2 major shorelines here in Lake Coyote at 1295 and 1278. And then there were 2 sills. These are like the edges of the bathtub here. One here kind of to the east and one to the north. And these showed evidence that they had been eroded and that water had spilled out of those. And so this figure here just kind of shows us the ages again, summarizes the ages again. So we have at least one older shoreline from a higher stand that doesn't appear to be kind of probably related to the flood we were studying. It's older. These are all probably about the same age based on the kind of the soils and weathering characteristics. And then that's the same thing, this shoreline here in Coyote, older than the lower shorelines. Okay, so a rush and a gush. So I can't forget to tie this into a rush and a gush. So here's our gush here. And the gush, we would have had Lake Alvord rising up and then eventually rising up to the point that it spilled into the saddle here at Big Sand Gap and flowed through the saddle and went into the Coyote Basin. So it looks probably something like this, where we had a high stand of Lake Alvord. And then eventually, as it rose, there was some sort of failure here this is at Big Sand Gap, and that spilled into Lake Coyote, which probably held a lake, and just would have overwhelmed it. It would have you dumped a ton of water in Lake Coyote, it couldn't have held that, and Lake Coyote spilled out. And so this is a map here just showing us kind of Lake Coyote, the edge of Lake Coyote here, and it would have had 2, so we see the shoreline here mapped out, and we had an outlet that water would have traveled north, and water would have traveled east. And as it flows out of here, the topography kind of around here is really flat. So we don't see any evidence of flooding. We think the water just kind of spilled out as big, broad, what we call overland flow. So there was no channels there to channelize it, to funnel it all in. But eventually it reached a drainage called the Crooked Creek, and it flowed down the Crooked Creek here. And we estimate that the flood would have released about 20 cubic kilometers of water. And so if you just think for a moment, if you think, a kilometer, a little more than a half mile, right? That by that 20 times, that's how much water we're talking about. And it would have taken about 3 days. The flood would have gone on for about 3 days. And we really see some of the spectacular evidence of it downstream as it channelized in the Crooked Creek here. And that's what we're going to look at next year. So this map here is showing us the flood inundation. That's what's in blue. And then the triangles are showing us some what we call paleo stage indicators. So these are like those erratics we saw earlier with the Missoula floods, representing the surface of the flood. And then these bars here, these would have been sediment deposited at the base of the flood here. We're going to look at a couple of these. This first one, named the Stoddard Bar after a ranch, the Stoddard Ranch. And so this is the Stoddard Bar here, and you can kind of see how it rises up in topography. It just gives you an idea of the landscape here. And as you go and as you walk up on this area here, this is what you get, this jumble of boulders. And these things are, some of them are over 6.5, 7 feet in diameter. So these are, it's going to take a lot of water to move those. And then we move on further down and come into Anderson Bar here. And to me, this is some of the most spectacular flood evidence here. So here what we're seeing are some large boulders that are imbricated. And maybe you've seen before imbrication, if you've looked at a stream bed and you've seen rocks kind of like dominoes, almost like dominoes that have fallen over in the direction of flow. And you can see how these are imbricated. They're like dominoes that have tipped over here. And here's Cassie in front of one and sitting on one to give you an idea. And here's me on one of the largest ones. And these things we measured over 4 meters in diameter. Okay, so we're talking over 12 or 13 feet boulders that would have been moved by this flood.
How far did they roll?
How far do they roll? Yeah, it's probably not too far for a couple reasons. We think we found the plucked surface a few hundred meters away. And then the other thing we notice here is the boulders still have really angular edges, right? So that implies that they hadn't been rolled or tumbled very far. So not a great distance, probably. Yeah.
What's the difference between a bar and an erratic, and where did the erratics originate from?
Great question. So the question is, what's the difference between a bar and an erratic? So an erratic is going to be it's going to be a rock that gets transported by the flood and gets deposited, and it's not it doesn't have the same, it's not the same rock type as that local geology around it. In bars here are going to be they're going to be sediment deposited generally on the bottom of a stream or along a side of the stream where the velocity of the stream slows down. Okay, so in many cases we'd find these bars at the mouths of steep narrow canyons. Okay, so the water would have been rushing really fast through that narrow canyon, just like you put your thumb over a hose and the water flows really fast, and then you release that thumb and the water spreads out, right, and slows down, the velocity decreases. So that's kind of the same thing here. You would get this kind of rush of water through these narrow canyons, and then as the canyon basically terminated, the water would slow down, deposit the sediment.
What was the origin of the erratics that you showed us?
Yeah, so the erratics for this flood would have been just they would have been rocks that would have been plucked, smaller rocks that would have been plucked further upstream and then carried a greater distance. So they're a lot smaller.
But what about the erratic park?
Oh, the erratic park, yeah. So that was with the Missoula floods. And so that was a rock that probably came from like Canada and carried in these icebergs all the way in one of those floods down. Yeah. Further downstream here, we have another set of bars here, the midden bars we call them. And they're smaller here. We can see smaller clasts, but what we do find is a kind of a different, 3 different terrace surfaces here. And so this could have implied maybe these were deposited in 3 different floods, or we had one big flood that came, and then as it kind of slowed down, as this velocity slowed down and waned, it would have deposited these lower terraces. And I see in Zoom here, the orange reference, that's my field notebook. So it's just a small field notebook, you know, maybe 7 inches, 8 inches for scale, yeah. This figure here shows us the flood route. So the line here is the elevation of Crooked Creek, okay, the base of the stream, the modern stream. And the triangles here represent flood evidence that we found. So this shows us here how, you know, it can kind of show us how high the flood surface was relative to the creek. And we can kind of see we have stuff right around in here that's pretty darn, you know, we find it up pretty high above the present day channel here. Okay, so that's some of the evidence for the flood. And then we also wanted to try to figure out the flood's discharge. And the discharge is the volume of water that's pouring through a given point per second, okay? And so geologists, when we're looking at streams, when we're looking at flood, the discharge is a way to tell us how big that flood was. And so we did a modeling technique here that's been applied to the Missoula floods and to the Bonneville floods here, called the step backwater technique here, and it uses a kind of an Army Corps of Engineers modeling program to figure this out. And really, what we're trying to do is we put in our flood evidence, the elevation of that flood evidence. And then we can kind of do pretend floods on this modeling program. So we can say, what if we did a flood that was this big with this much discharge? Does that surface of the flood match and fit our flood evidence here? Okay, and that's how we can figure out that's how we figured out how big the Missoula floods were, how big the Bonneville flood was. I mean, even today, just for like practical purposes to figure out, you know, meteorological floods. This is the Corps of Engineers and hydrologists use this same technique, similar technique. And what we found, the first place we wanted to model was the outlet between Alvord and Coyote, okay? Because that's going to kind of control how much water, you know, how much water there, that's, you know, there shouldn't be any more water downstream. And when we did that, that was about 10,000 cubic meters per second. When we modeled down in the Crooked Creek in this area here, so this is you know, way down in the flood, kind of by the Stoddard bars, we get 40,000, and we're like, well, something's not right, okay? Either we measured something wrong, because that's like 4 times greater than what it should be. It shouldn't be more than 10,000 cubic meters per second. So we did some thinking and some head scratching, and we were like, well, wait a second, we had older shorelines in the lakes. Maybe we're looking at an older flood, okay? So maybe that is evidence for an older flood. The other thing that I played around with is, what if as the flood came, it caused a whole bunch of erosion of the base of the channel. And it turns out that it would, if we eroded the channel by about 13 meters during the flood, our discharge would match our flood evidence here. So not quite certain. We know that there was at least one big flood, probably evidence for this higher lake stands of older floods. And maybe that's what we were getting at here, bigger, older floods. Okay, the last thing is, like, how old is this thing? How old is this flood? And it's tricky to date these floods. And around this time, there was this new form of dating coming on, and 2005, 2006, called cosmogenic dating that's widely used today. And so we decided to try to apply this type of dating to flood boulders here to figure out the ages. Now, the way this dating works here, it's not like carbon dating. The way this dating works here is you can measure when everything, including us right now, we're getting bombarded by cosmic radiation from space, okay? And so if you have something that wasn't exposed, like a rock that wasn't exposed, like inside, in an outcrop that wasn't exposed to cosmic radiation, and a flood comes along and rips off a surface, that's when a flood comes along and rips off that surface, it's going to start accumulating that cosmic radiation. And so this technique is kind of measuring that, okay, using helium isotopes as just kind of like that proxy to measure the cosmic radiation. It's good on glaciers too. You can imagine you had like a glacier, whole bunch of ice on a rock, and then that ice melts away and cosmic radiation is going to start accumulating. So you're not measuring like the age of the rock, but you're measuring the age of when the glacier melted or when the flood occurred in this case. And so we dated some of these bars here, and unfortunately, these are rocks from all one bar, and we're getting numbers from 28,000 to 171,000. So kind of all over the place. And this is like the story of science, the story of geochronology. A lot of times is it's really difficult to get good dates. You need kind of like the stars to align sometime. So this didn't really help us. But it was a great experience to learn how to do this. So I was talking to Mara Threeheis one day on the phone, and she's like, who again worked for the USGS and spent her whole career studying Great Basin lakes, these pluvial lakes. And she said, well, Deron, one thing to look out for is ashfall, old ashfall. I found a ton of old ashfall, all in like lakes in Nevada and Utah, and that's a great tool that you can use to date. And so one of the last times I was down there, I was kind of checking out an area that had some finer grained sediments, and I knew there were lake sediments for Lake Alvord, and I was just kind of throwing up my hands at this point, kind of frustrated about figuring out the age of the lake. And one of the reasons I chose this project is besides geology, I'm just like a naturalist at large. I love being outside. I love plants and animals and learning about them. And I was keeping track of all the lizards that I was seeing. And there was this one lizard that I was reading, the Great Basin collared lizard. It has a white collar around its neck. And it's rare in Oregon, but you can find it in Alvord Basin. I was like, oh, I just want to find one of these. And I was walking around and I was kind of looking through these lake sediments here, and I looked up and I saw a collared lizard. I was like, oh, this is awesome. And then I looked down and I found this white layer right below me. And this is ash. This is what we call tephra, and you can see it right here. And there's a couple layers here. And I was like, oh, jackpot. And so I take some, and what you're able to do with ash here, or tephra, it's called. Tephra is just the all-encompassing term for material that's ejected out of a volcano. You can analyze it and measure its chemistry. And there's like a database, basically, we have of all these ash layers that have been dated. And you can basically it's kind of like CSI, right? You can kind of match the ash you find, the chemistry of that ash with, kind of this database of older ashes. And this turned out to match really well with an ash from Mount St. Helens. It's about 13,000 years old. And so this is it's called Set S, Mount St. Helens eruption. And you find it in the Missoula floods too. And so we know here that the lake would have been, there would have been water in the lake. The lake sediments that I found in Lake Alvord with the ash layer happened after the flood. So we know that the flood had to happen a little before 13,000 years. So this lake would have been there. Mount St. Helens had this big eruption, ash dumped down. The other thing that we found in the same lake sediments were diatoms, and we had those analyzed, and diatoms are microscopic plankton. And we had them analyzed, and they turned out to be a species that was an open water, what we call an open water species. So they were freshwater. Okay, so that implied that they would have been a species that would have existed when the lakes Alvord and Coyote were connected, because you'd expect more of kind of like brackish or saline water if the lakes weren't connected there. Because remember, it's a closed basin, and so there's a lot of evaporation, and so the water, like the Great Salt Lake, right, it's salty. So you'd expect a different species there. So those diatoms also helped us kind of nail down the age too, because the lakes the flood had to have happened if those diatoms were present around 13,000 years. So what we found here is we found this Lake Alvord released a flood of 10,000 cubic meters per second. It's around 13,000 years. And one of the cool things about this is it's one of the first times it's recognized that we have a connection between the Great Basin and the Columbia River here in this case, because this flood flowed into the Owyhee River. The Owyhee River flows into the Snake River. Snake River flows into the Columbia River. So on this research, where it's mostly been cited as biologists interested in a pathway for fish to move in from the Columbia into the Great Basin for migration. So I was just absolutely honored to do this project, being a native Oregonian, getting to learn and contribute a little more to the knowledge and the history of our state. And what I want to leave you with here today is I spent a lot of time thinking and about some of my predecessors here, like Brett's, and just want to leave with this quote that really spoke to me and just makes me think of being out in the Alvord Desert. Let the observer take the wings of the morning to the uttermost parts of the earth. He will nowhere find its likeness. Thanks. All right, so do we have time for questions, or how are we doing on time? I know there were some questions out on Zoom.
Yeah, there's a couple.
Okay.
Well, let's see. Couple people were wondering about the source of the basaltic boulders in the bars.
Yeah.
From the steams.
Yeah. So right. So the source, like where the basalt came from itself, wasn't actually. So Steens is kind of interesting because Steens is actually the Columbia River basalts. The basalts where these came from weren't Columbia River basalts. I want to say they're younger than Columbia River basalts, 7-8 million years ago. And you know, I think their source, I'd have to go back and recall their source, but you know, we find it's not atypical to find basalts in the Great Basin because there's a lot of spreading going on, and where there's spreading going on, you're you know, basically you're relaxing pressure on the mantle, and that can cause volcanic eruptions and basalt and lava, you know, kind of basaltic lava. So that's not atypical to find in the Great Basin. Yeah.
The Missoula, probably the Bonneville, those were ice dam catastrophic failures.
Right. So the Missoula was ice, and Bonneville wasn't ice, but it was just similar to like this one. So it was like the bathtub analogy, right? So it's just spilling out.
I guess I'm having a hard time imagining a catastrophic flow like you're talking about, with an overflow of melt.
Yeah.
It's like you start to just over time, just a river cut, and water leaving the river cut, not a catastrophic.
Yeah, it's hard to imagine the sky. I agree. And that's how we often think of water flowing, and that's, you know, kind of the gradual. I mean, that's one of the great. It's such a great question, because that's, you know, that's kind of two ways to think about things in geology. There's like gradualism, where some, rivers we think are cutting their canyons, and that's a very slow process over, millions and millions of years. And then you have these like catastrophic floods, which are much more, as their name implies, catastrophic, very quick and rapid, and just don't really have time to do that work in some cases. But we do see with the Missoula floods, we do see, just these individual floods carving channels because they were so massive. And the Missoula floods were certainly some of the largest floods ever on our planet, probably. Yeah. Question here, and then I know we have someone in the back. Yeah, go ahead.
So when you're talking about these catastrophic floods, one way to tell them would be how straight they're going.
Yeah.
Because a meander is like a slow moving stream. So you have to have something that's going to direct it specifically.
Exactly.
My question though is more along, what is the underground hydrology of that area?
Yeah.
Repeat the question.
Yeah. Oh, thank you. Yeah. So the question was really around what is the underground hydrology of the area? And I didn't really look into that or study that too much. There were along Crooked Creek. I spent a lot of time hiking the whole length of Crooked Creek, looking and mapping flood deposits, and there were some just beautiful springs along there. So the water table was pretty near the surface, I would imagine.
Well, if you were parking near hot springs.
Yeah.
That would
Yeah.
make total sense.
Exactly.
So I'm just trying to figure, when you're talking about a catastrophic flood, you're also talking about the ground collapsing underneath it as well.
Yeah.
And that area is riveted with lava tubes.
Yeah.
So you're going to have the ability for the ground to collapse at the same time.
Yeah, absolutely. Yeah, absolutely. Yeah, thanks. Yeah, we had another question. Sorry. Yeah.
Could things like that have happened also in Lake County with Lake Neighbor, water wetlands?
Yeah, great question. Yeah, so the question is, could have this happened with other lakes like Lake Abert, other of these pluvial lakes? So I'm glad you brought that up. So Meredith at a conference recently just gave a great talk about that we really see a lot of the Great Basin lakes during the last ice age were in sequence. So they rose at the same time and they came down. Like we saw with the Alvord and Coyote, we saw an older lake stand and then it had to probably drop and then rise up again. And when we think of the ice age, right, we think of like this big glacial period, but really kind of the last 2 million-ish years or so, we've been in this ice age, but it's been punctuated by these cold periods and warm periods, longer cold periods, shorter warm periods, where glaciers are advancing, receding. And the lakes follow that record somewhat too. And so I think my answer is, I think if people started going around and looking, I think we'd probably find some other, same things where lakes are going to rise up, they're going to do their thing, spill over, and these are in remote areas. And so it wouldn't surprise me at all that this isn't unique to Lake Bonneville or Lake Alvord. Yeah. Maybe like 20 years ago,
Not too late.
So Carrie kind of had a similar question, and maybe Carrie, do you want to unmute if you have a follow-up or want to say something else? You're muted, Carrie.
And actually, if you guys could stop the PowerPoint, that would help.
Oh, sure.
And I know I'm echoing here, but my question is, the follow-up is other large floods here in central and eastern Oregon, because we have evidence of large quartzite cobbles in the Paulina Basin, and they're definitely piled up. They're big bars, and it's, where did they come from? What was the source of the water that rolled these pretty good sized cobbles around? And I think this is awesome about the Coyote and Alvord. So thank you.
And Carrie, where are you located? Where are these cobbles geographically?
East of Prineville, near the town of Paulina.
Okay. Yeah, I mean, there's the Deschutes formation out there. Yeah, I don't know. Yeah, east of Paulina. I don't know. Yeah, interesting.
If I can make a comment, those are part of the Bernard Formation, which is Cretaceous in age.
Okay.
Actually, these are probably not. The fellow that was doing a little research on that found the Bernard, but these are a totally different deposit.
Okay, yeah, because the Bernard has lots of quartzite cobbles in it.
Yeah.
Yeah, there's there's the Gable Creek formation, but I don't know, you see that more around Mitchell, that is Cretaceous, and I think that may have some cobbles.
Dr. Sharon.
Oh, is it on this here? Oh, okay. Let's see, I might need some help here on
Yeah, I'm
Is it
not sure
this?
either.
the sharing content.
Yeah.
But yeah, the Gable Creek formation, that's a conglomerate also. But yeah, I don't think of that so much by, that's kind of over on the other, thanks Sheila, on the other side of the Ochakos there. So, yeah.
Yeah, thanks. It was a really good talk. Putting together some thoughts on time and the like, and we talk about the glacial epochs, and we talk about 2 million years or so of glaciation going on, and actually the Missoula floods are just the last 2,000 years, 17 to 15,000 years ago.
Yeah, about 17 to 15,000. Yeah.
And like Bonneville of 15,000.
Yeah.
And 13,000 for stuff that dumped into the water. So
right.
Amazing that there's been so much water that's been held up and then just gushing out here.
Yeah.
The Missoula exploding
7,000 years ago, right.
So it's like, there's so much activity in that whole
Yeah.
area.
Yeah.
It's not surprising.
Yeah. And it's, go ahead, Scott.
Just in response to the ages on the Missoula floods, we now say 15 to 19,000.
15 to 19,000, yeah.
But we have a Friends of the Pleistocene trip coming up in the fall, and we're going to be exploring, in my book, we call them ancient cataclysmic floods, evidence of Missoula floods all throughout the Quaternary.
Right. Yep.
And there may be 10, 20 different ones over that 2.8 million years. And they all have caliche in them. And Erica Medley, one of my students, did a thesis on these sites. And then we are focusing in the fall, Friends of the Pleistocene, going out looking at some of these with Vic Baker and Bruce Bjornstad and a guy from up in Montana. Okay. So throughout the Quaternary, we have all these catastrophic floods.
Right. Yeah. And it's just, I think a consequence of having that ice sheet and damming, damming things up. And these catastrophic floods are really common throughout the West, because really, I think you 3 ingredients. You can have ice can do it, like an ice dam. You can have lava do it too, lava dams and landslide dams too. And those are all really common, right? Because we're certainly in a volcanic province here, and and then just with the topography of the West here, right, too, landslides are quite common.
So Cheyenne was just wanting to clarify what was the source of this 20 cubic kilometers of water?
Yeah, so the source here are the lakes, are going to be Lake Alvord and Lake Coyote, where the source is. So like the Bonneville flood, so the source of those two like that. So it's the lakes.
We'll take one more question and we have it up here.
Sure.
Referring back to the Bonneville Lake flood and the big sand gap.
Yep.
And we saw pictures of the strand lines.
Yep.
They were way up there.
Yep.
So the ice dams from Missoula would come down, goes off, go down. How did the drainage work out of big sand gap?
Yeah.
Did it overtop the road?
Yeah. No, it's a great.
What was the difference
Yeah.
between the top height?
Yeah.
And the bottom of the sand gap was in terms of cubic and also rapidity of drainage.
Yeah. So I'd have to, off the top of my head, I don't know the elevation difference from the very top of Big Sand Gap. Well, no, I do. So it would have been, it would have been about, I think 12, 13 meters actually. Okay. From the top down to the base of Big Sand Gap or so. 12 to 13 meters, I think. Yeah. Yeah.
Not a
Yeah.
big drop like
Yeah.
700 or something.
Yeah. So this, I mean, this flood, while significant, if we think about it, if we compare it, it's like nothing to the Missoula floods. And Scott, help me here. Is the Missoula flood discharge 17 million? Does that sound?
Yeah.
17 million cubic meters per second. Bonneville, I think, was about 1 million cubic meters per second. And this, we're probably looking at, we know 10,000, maybe there are older floods at 40,000. So really this, it did significant work. And I think it's important to point out that, kind of these intermediate magnitude or intermediate size floods still do significant work. It's not just the big ones that do everything here, but, when we compare it to like Missoula and Bonneville, it's a pretty small one.
So is it necessary for the Big Sandy Gap to have collapsed in order to have that flood?
Yeah. So yes, because when we're looking at the shoreline elevations, right, of Lake Alvord, in order to build the shorelines, Big Sand Gap had to be closed, right, at that same height as the shorelines we're seeing in Alvord, right, to develop get a lake to road and deposit and develop those shorelines. And then we see that drop there too. Yeah. All right. Thanks so much.